Okay guys, so this is going to be the video for lab 2 over momentum. So the basic idea, the ideas that we're trying to get across with this lab, first off, is that what is momentum? And momentum is the product of mass times velocity. So it's some quantity that we use, and it's convenient because of this idea that the fact that momentum is conserved. So anytime that we have a collision, the momentum before the collision, the total momentum before the collision of the two objects that are colliding is going to be equal to whatever the total momentum is afterwards, as long as there's no other additional external forces acting on the system. Okay, so we have two examples of two types of collisions, and we're going to use this idea of conservation of momentum to see which type of collision would result in our second object here moving faster. Okay, so our scenario is this. We have two objects, object 1 and object 2 here. They're just balls, all right? Object 1, before they collide, is going to be moving towards ball 2, and ball 2 is going to be stationary, so it's not moving. For an elastic collision, after they collide, the two balls will bounce and then travel in opposite directions. Okay, and this one will travel with some velocity we'll call v1 prime. All right, with this prime, just we're denoting that it means it's after the collision, and then this one will be traveling with some velocity v2 prime. Right, and this ball here initially is traveling with velocity v1, and then this ball 2 has a velocity v2, but that velocity is equal to 0 because it's not moving. Okay, and now we want to use, again, conservation of momentum, which is just the idea that the total momentum before and after is the same, to then find what is the velocity of this second ball in the case where they bounce. And then we're going to compare that to, okay, what happens if after they collide, instead of bouncing, ball 1 is now stationary. So that would mean that in this case, our v1 prime is now 0, and this is still v2 prime. And in our case, before the collision, nothing has changed because what happens before is the same for both the elastic and the inelastic collision. So this would still just be v1, and then of course v2 is still equal to 0. Okay, so let's use conservation of momentum to find out what is this final velocity going to be, because whichever scenario results in v2 being bigger, v2 prime being bigger, that's going to be the case where it's going to travel the furthest, or the object 2 it will travel the furthest. Okay, so the total momentum of our system before the collision we can write as momentum before, and it's going to be the sum of the momentum of object 1. We'll just say that both of these objects have a mass m that's the same, so they have the same mass. So we can just write it down as m v1. All right, that's the momentum of the first object plus m v2. All right, well, we know v2 is 0, so this whole term is 0, so we can ignore that. So the momentum before, the total momentum before, is just going to be equal to mv1. All right, now let's write down the momentum afterwards in a similar way. So we have momentum after is going to be equal to a minus mv1 prime. It's minus because velocity is a vector, remember, so that makes momentum a vector. So since v1 is pointed to the left, and as we learned in the first week, we can consider to the left to be negative, and we'll say to the right as positive. So if we're moving in the opposite direction, it comes with a negative sign. So negative there, plus mv2 prime. Okay, and don't let this prime confuse you. It's just notation that means after the collision. Okay, so it's just a way that we're denoting that this is after the collision. All right. So now what we're going to do is use conservation momentum and say that the momentum before, so P before, is equal to P after. And if we do that, we can see that mv1 is the momentum before is equal to minus mv1 prime plus mv2 prime. All right, we can see that all of these have the same mass, so we can cancel the mass out, just divide both sides by m. And so what we're left with is v1 is equal to minus v1 prime plus v2 prime. And then if we remember, what we're looking for here is v2 prime. So if we solve this equation for v2 prime, what you get is v1, which is again the momentum of the object, of the first object before the collision, plus v1 prime, which is the momentum of the second object, or sorry, the momentum of the first object after the collision. So that's what the velocity of this second ball is. And I think I was saying momentum before. I'm sorry, I meant velocity. So v1 is the velocity of our ball before the collision, first ball before the collision. v1 prime is the velocity of our first ball after the collision, and v2 prime is equal to the sum of those two velocities. All right, let's do this same thing for the inelastic case, and then we'll be able to compare the two velocities to each other. Okay, so our momentum before doesn't change because nothing has changed here, so let's just rewrite that. Momentum before is just going to be equal to mv1. All right, and then our momentum after is going to be mv1 prime plus mv2 prime. But remember, v1 prime is now 0 because it stopped, whereas before it was going to the left. In an inelastic case, it stops after it collides. So this is actually 0. So my momentum after is going to be equal to mv2 prime. All right, and now if we use, again, conservation momentum to set our momentum before equal to our momentum after, what we'll get is mv1 is equal to mv2 prime. The masses can cancel out because they're the same. And so what we're left with is v2 prime is equal to v1. All right, now if we compare the velocities of our object 2 after the collision, you can see that this one has an additional amount added to it, v1 prime. Okay, whereas this one, v2 prime, is the same as v1. So in this case, for inelastic, the second object will have the same velocity as whatever the velocity the first object had before the collision. In the case of the inelastic, the second object will have whatever the velocity of the first one after the collision plus the first one before the collision. So you can see that inelastic is going to have a greater velocity after two objects collide. So there's a greater amount of, not a greater amount of momentum, but because this object goes in the opposite direction, object 2 is going to have a greater change in momentum, or it's going to have a greater velocity. And that's what we want to show in this experiment. So what we're going to do is we're going to have two different types of collisions, the elastic and inelastic, and we're going to see is this true? All right, does an elastic collision result in our second object traveling faster and that's going farther than the elastic as we just showed? Okay, so if you didn't quite follow the math, that's okay. All we're looking for here is this, all that's really important here is this final conclusion that in an elastic collision, our second object goes further than it does in an inelastic collision. Okay, so what you'll see next is we're going to be in lab, and we will kind of try to show how you would go about proving this idea. Okay, guys, so this is going to be the exploration part. It's going to demonstrate the exploration part of Lab 2 of momentum. So the very first question asks you to make some observations about what they call a happy ball and a sad ball, and what type of collision that might be. So one of these is going to be a happy ball, and one of them is going to be the sad ball. Okay, and the happy ball is going to be the elastic ball, so that means it's going to bounce when we drop it. Okay, and the other ball is going to be what we call sad, which means it's going to stop when it hits the table. So it's going to collide inelastic with the table, means it stops, and if it bounces, it's going to collide elastically with the table. So we'll go ahead and drop these, and you see one very clearly bounces while the other one clearly stops. And so with that, you should be able to make answer all of the questions that you need to in that first part of the exploration. The second part of the exploration deals with dropping two balls. One is much heavier than the other, right? So we're dropping a basketball and a ping pong ball. We're going to drop them directly above each other. When the basketball hits the ground, first it's going to bounce up and then collide with the ping pong ball, right? And they're going to both transfer momentum to each other, but you're going to see one of them move much faster. It's going to have a much greater change in velocity. So the question is, why does one have a greater change in velocity versus the other one, right? Even though they're transferring the same amount of momentum, all right? There's going to be a momentum transfer between the two. So let's go ahead and drop these two balls and we'll make our observations. All right, so you can very clearly see that the ping pong ball has the greater change in velocity, and so it's going to be up to you to determine or to come up with some reasons why you think the ping pong ball will have a greater change in velocity versus the basketball. Okay, and that should be all the information that you need. All of the masses are given to you in your included data sheet on Canvas. The next part of this video, you're going to see us actually performing the experiment, which is where we're going to show that an object hit by an elastic dart is going to travel further than one hit by an inelastic dart. Okay, so we've got the experiment for our Lab 2 set up. What we're going to do is we have this dart here. Okay, and this dart you can see has a little focus. Anyways, it has an elastic end, which is not going to bounce. And on the other side here, it has an elastic end. Okay? And so what we're going to be doing is we're going to put this pendulum, or what they call the dart, and we're going to hook it up to this pole over here. And this pole is going to allow us then to pull this dart back and then to strike our cart that we have here. Okay, and so what we're going to do is we're going to strike it 3 different times. We're going to want to make sure that we measure the height of this dart carefully so that we're dropping it from the same height each time with each end. So we'll do it 3 times with the inelastic side, and then we'll switch this guy around, and then you would have done it 3 times with elastic. Now, just like last week, I'm not going to make you sit through all of those trials. The data is already provided for you on Canvas, but we will just make 2 different demonstrations. So let's try the elastic side first, is what it's set up on. So this is going to bounce off of the cart after we lift it up. So we're going to come to right about there, and if we let it go, it's going to travel some distance, right? And then we would be able to then measure that distance. We would do that 3 different times. Now, you would be doing this more carefully, and you would be measuring the height each time, but since this is just for demonstrations and I'm not actually taking data, I'm just going to lift it to about the same height that I did last time. And this is for the inelastic side. And you can see it clearly goes less far, or not as far. Okay, and this is again because the change in momentum of the dart is less whenever it stops versus whenever it comes back and then goes negative, okay? And that change in momentum of the dart has to be transferred to our cart. So because the inelastic has less change in momentum because it stops versus hitting and then going back, the cart is gonna go less far, okay? And it goes back to, again, that initial calculation that we did at the beginning of the lab, where you could see that V2 prime, which would be the velocity of the cart, is going to be less for the elastic and more for the, less for the inelastic and more for the elastic. Okay, so like I said, all of the data that's been taken is on Canvas. You can do all the necessary analysis and answer all of the necessary questions with that data and what you've seen in lab. All right, we're going to go ahead and end it there. We will see you next week.